We've been working with partial fraction setups to help us solve some integrals, and in the last video, we saw maybe a new setup for you. We saw what happens when we have these irreducible quadratic factors in our denominator. How do we set up partial fractions for that situation? And here you can see maybe this is a new situation for you. We have these linear factors, but now we have repeating linear factors. So we have x plus 1 squared now. We want to know, how do we set up partial fractions for this situation? And again, a good first question to ask ourselves is, why are we even thinking about partial fractions here? And it all goes back to, okay, we have a greater degree in our denominator than in our numerator, and then also nothing else can be factored here. So we can't eliminate anything else. So that leaves us with partial fractions. And let's pull out this integrand and start working on it and talk about what its setup is going to be. So we have this here. There's our integrand. And writing this out, maybe you want to pause the video and, using what we've talked about already in some previous videos in partial fractions, you want to try to play around with this and figure out what its setup is. All right, maybe you've played around with it for a little bit, and maybe you tried a few things. You might have said, okay, I know how to deal with linear factors, and you might have said, okay, let's try this out. Let's try a over x plus 1 squared. Let's try that out. And it's a good thought, but you can see when we clear these denominators here and we set up some coefficient equations, we'd say that a is 2, and you can see that these are not equal, that we're missing some information from this left-hand side still on this right-hand side. So that is a good thought, but that will not work. And maybe from the last video, you would have tried something different. You would have said, okay, I have a second degree in my denominator here. So when I write this out, I'd have x plus 1 squared. And you said in the last video that I need 1 degree less in my numerator. So maybe you would have tried, okay, let's try ax plus b. And you can see here that we'd have a is equal to 3 and b is equal to 2. So we'd literally just be writing out the same thing that we have on this left-hand side. And it wouldn't help us out in solving this problem at all. But it was a good thought. It was a good thought. So you've tried, and those were good attempts there. But now I want to write out for you what the partial fraction setup is, and hopefully I can give you some intuition after I do so. So the partial fraction setup for this is going to be a over x plus 1, and then we're going to be adding on, we're also going to have plus b over x plus 1 squared. This right here is our partial fraction setup. And hopefully I can give you some intuition on this. Maybe you can make an analogy between this and decimal expansion. You could think of this in terms of like decimal expansion. So if I were to give you the decimal 0.123 and say, give me the decimal expansion for it, you would say, okay, that is going to be 0 over 10 to the 0 power. And then we have plus 1 over 10 to the first power, plus 2 over 10 to the second power. And then finally, I got ahead of myself, 10 to the second power, and then finally plus 3 over 10 to the third power. That is this decimal expansion here, and we cover all of these degree terms to get this decimal expansion. So similar thing going on over here. And then maybe you buy that, but maybe you remember from the last video I said, okay, when you have a second degree kind of denominator here, second degree denominator, you need to have 1 degree less in this numerator. And you'd say, well, that's not happening here. We only have b. So what's going on with that? And I want to show you there is no contradiction. And you can see that when you get a like denominator here. So if you were to get a like denominator, you would have a, and then you'd have times x plus 1, and then you'd have plus b, if we're getting like denominator, and then you'd have over x plus 1 squared. Just getting a like denominator here. And now you can see we do have this condition that we talked about in the last video, that we have 1 degree less in this numerator. So everything checks out there, and hopefully you can feel good about this partial fraction setup. Now, what we want to do is solve this. We want to find what a and b are. And a good first question to ask is, because my goodness, we love that cover-up method, is can we use cover-up to find either a or b? And the answer is yes, but we can only use it to find b. Let's use that. Let's use it to find b. And in order to find b, we're going to let x be equal to -1, just using some cover-up method. And if you haven't seen that, go check out that video. So if we let x be equal to -1, On this left-hand side, we're going to evaluate this numerator at x is equal to -1, and we'll find that b is equal to 3 times -1 plus 2, and this comes out to -1. So we found b pretty quick. Now we're wondering, okay, how do we get a? And in the last video we saw we cleared this denominator and set up some equations that represented the coefficient terms on the various degree terms that we had access to, and we're going to do the same thing. So let's clear this denominator, x plus 1 squared, and then x plus 1 squared on this right-hand side. All right, so denominator cancels, and we get this. We have 3x plus 2, and this is equal to, we're going to have an a, we have a times x plus 1, a times x plus 1, and then these are going to cancel, so we're just left with b. So this is plus b. And then we can continue to expand this out a little bit. So we have 3x plus 2 is equal to ax plus a, and then we have plus b. And again, we want to set up some equations here that represent their coefficients. And we're after a. We already found b, so we just need to find a. And nicely, we can look at this first degree term here. This first degree term, we have an a, and we only have 1 on this other side here, and that's 3. So we have a is 3. We can just write it down. So that is pretty easy for us. So we find that a is 3 here. So now we have a and b, and we just need to come back up here and write out our definite integral, our indefinite integral now. We found that a is 3. So a is 3 over x plus 1. All right, and then we have plus b we found to be -1, so this is -1 over x plus 1 squared. And all of this is being integrated with respect to x. And again, once we get to this point here, solving this integral is fairly straightforward. We already have the tools, and we've already had a ton of practice on how to do this. You could split this up into 2 separate indefinite integrals, and you could solve each independently. And with this first one here in green, we could just write down the answer. This is 3 times the natural log of the absolute value of x plus 1. And then this other one here, you could go through use substitution, or if you had some practice with it, you can just write it out. This is going to be plus. This is going to be plus. I wanted that in pink. Pink, please. There we go. Plus 1 over x plus 1. And then we can't forget our c value. If you don't believe me on this, you could just differentiate this, and you'll see you'll get this up here. Now, there is our answer right here. But really, I wanted to show you how we deal with this type of partial fraction setup where we have these repeating linear factors in our denominator. And we saw this to be the following. And again, it's a good idea, if you forget this, to just think back to, okay, this was kind of like decimal expansion. So hopefully that can help you remember this in the future. And we'll get some more practice in the next video.